Hello, welcome to my talk on stability of floating structures. Part 2, Practical Requirements and Standards. In this talk, the calculation of the restoring moment and the relevant rating arm in large inclination angles will be given, and a simple numeric method is also introduced. Then I will introduce some important standards, including static and dynamic stability standards for the floating structures. Finally, I will introduce the stability, or more specifically, the initial metacentric height and the requirements for the motions of the structure in waves. In the first part of the talk on this topic, the initial metacentric height Gm was introduced. Here, I will introduce yet the other important concepts, the restoring moment M and the related rating arm Gz, especially in the large inclination angles. And these important parameters are related to the stability of the floating structures, and we will see whether the floating structure has the ability to self-restore to the upright floating position. For this purpose, I will present the coordinate transform first. Suppose the structure has a heel angle phi around the x-axis. In the plot, this is an axis pointing out of the screen, and the coordinate transform would be given by this. So the new coordinates x prime, y prime, and z prime would be given by these formulas. And we see in this case there will be no change for x, but y and z would be different using this coordinate transform. Similarly, if the inclination is around y-axis with a trim angle theta, the transform is given by this formula. So there might be a question, what is the use of such a coordinate transform? The answer for this question would be the calculation of the new position of the center of gravity when the floating structure has an inclination phi. Now the center of gravity is given by the new coordinates x prime g, y prime g, and z prime g. And this new coordinates will be used for calculating the center of buoyancy, which will be seen later on in this talk. Similarly, if the transform is made on y-axis, and the center of the gravity would be given as this. For calculating the restoring moment in large inclinations, I would introduce a numeric method here, which uses the same panels as those employed in watt-meter analysis. Details can be found in the reference. Here, watt-meter is an important code for wave structure interaction, developed in MIT. Watt-meter short for Wave Analysis, MIT. See the figure, which shows the panels of a structure of a BBDB oscillating water column wave energy converter. The yellow panels represent the flows. These are normal panels, and they are wet only on one side. The cyan panels are the thin structures, which are wet on both sides. In the stability analysis, the thin structures are normally neglected, but for 1 meter analysis, they are very important. After the coordinate transform, following the formula in 1 meter, we can calculate the displacement here given by nabla x, nabla y, and nabla z given by these formulas. This displacement means we can calculate the structure displacement in 3 different ways. If the panels are correct and accurate enough, these 3 displacements should be same or very close. I used this check for my analysis for wave structure interactions to ensure the correctness and the accuracy of the panels. And then we can calculate the center of buoyancy, the rating arm, GZ curve, and GM, the initial metacentric height. The buoyancy center would be calculated using these formulas. This is important since the position of the buoyancy center is a key factor for calculating the stability parameters for the floating structure. Examine this plot. We can see in an inclination of the floating structure, there are 2 forces acting on the structure, the gravitational force and the buoyancy. Principally, they are equal in magnitude, but in opposite directions. Also, in an inclination, these 2 forces are not on same lines. Hence, they could form a force couple, and the distance between these 2 forces is GZ. So the restoring moment can be calculated as this. And we can see such a restoring moment would restore the inclined floating structure back to their upright position. And we can easily see from this plot, the rating arm GZ can be easily calculated by this formula given by YB minus YG. As an example, this figure shows the rating arm in different inclinations, the black line, and it reaches its maximum at about 40 degrees. In this plot, an approximation for the floating structure with the vertical wall when the inclination is less than 25 degrees. So the theoretical analysis GZ would be given by this formula. And from the plot we can see the calculation and the theoretical analysis of the GZ would be identical when the inclination is less than 25 degrees. This is a plot showing the rating arm and the floating status. At 0 degree of the heel angle, the gravity and the buoyancy forces are on the same vertical line, and they are balanced each other based on the Archimedes principle. At 20 degrees of the heeling angle, the center of buoyancy is on the right side of the center of gravity. Thus, these 2 forces form a force couple, and thus a pure moment, which could restore the floating structure back to the upright position. At 40 degrees, the rating arm reaches its maximum, and the buoyancy center B would be the farthest away from the center of gravity. Thus, a maximum possible restoring moment could be produced to bring the inclined floating structure back to the upright position. So at 8 degrees, due to the very large inclination, in this case, the center of the buoyancy moves to the left side of the center of gravity. Although the gravity and the buoyancy could form a force couple, but the corresponding moment is negative in this case, meaning the moment would bring down the floating structure further. Thus, the structure would capsize. In this slide, the two important parameters, the initial metacentric height, Gm, and the rating arm curve, Gz, are linked together. When the heating angle is small, say less than 5 degrees, the restoring moment can be calculated as this. Here, Gz is the distance between the gravity and the buoyancy force. Since in the small inclination, Gm would be a constant for a small inclination angle, so the moment can be calculated as this. Hence, we can obtain Gz given in this form and approximate it as this. Therefore, Gm can be calculated by this expression. Gm is the differentiation of Gz with regard to the inclination angle phi at phi equaling to 0. In this plot, Gm is calculated using the slope of the Gz curve at phi equaling to 0, and when the slope reaches the angle of a radian, that is 57.3 degrees. Theoretically, we can calculate the initial metacentric height Gm as presented in the previous slides based on the given center of gravity. But in reality, when a floating structure is built, the center of gravity might not be exactly the same as it is proposed. Generally, we need to carry out the practical inclination experiment to determine the initial metacentric height Gm. For doing an inclination experiment, we can put a weight, the capital M, on one side of the structure, as seen in this drawing. The structure would incline a small angle phi 1, and we have an equation for this inclination experiment as this. Here, L1 is the distance of the weight M from the center line of the structure. Next, we need to move the weight to the other side of the floating structure, see in this drawing, and the inclination angle is phi 2, and the corresponding equation for this inclination experiment. So if we put these two equations together, we have an equation given as this. Thus, we can calculate Gm expressed in this form. Using this expression, we can reduce the errors from the reference point for measuring L1 and L2, and the reference line, the vertical line, for measuring the inclination angles Here, we should be noted that the moving weight, the capital M, must be much smaller than the mass of the floating structure, such that the change of the center of gravity due to the moving weight would be very small and thus be neglected. Generally, for the floating structure, we must have enough stability so that the floating structure can survive in the sea, both statically and dynamically. For the static stability, a basic requirement is Gm must be positive. In fact, it should be larger than a certain value, for instance, larger than 0.15 meter, according to the standard. See the next slide. Also, the floating structure must have a positive righting arm for a certain inclination angle. Details can be seen in the next slide. The floating structure may also be subject to the dynamic forces. Thus, it would require the amount of the work done by the righting arm must be large enough according to the relevant criteria. In addition, the stability of the floating structure would be affected by the dynamic forces due to the waves, winds, and other dynamic events. In this slide, the IMO, the International Maritime Organization stability, is introduced. This is the standard for a ship shorter than 100 meters. This standard can also be used for other floating structures. For instance, the floating wave energy converters. In the item 5.1 point, the criteria are recommended, and it can be summarized as this. The area under the righting arm should be larger than 0.055 meter radians up to 30 degrees, and 0.09 meter radians to the inclination 40 degrees, or the flooding angle theta star F if it is less than 40 degrees. The area under the GZ curve between 30 to 40 degrees or between 30 to theta star F must be larger than 0.03 meter radians. The righting arm at 30 degrees must be larger than 0.2 meters. The angle of the maximum righting arm must be larger than 25 degrees, properly exceeding 30 degrees. The initial metacentric height, Gm, must be larger than 0.15. Take an example of an actual wave energy converter. We have two different GZ curves for the device due to two different arrangements. The older arrangement, the black line, and the new arrangement, the purple line. And we can check whether the new arrangement it is satisfactory. Based on the GZ curve, we can calculate the area under the curve using this formula. Here, it should be noted the unit of the area is meter radians. The calculation is given by the green line. In checking whether the floating structure can meet the standards for stability, we need to check the requirements of the items. based on the stability standards as this. The actual values are given in this column, so we can see the margin between the actual value and the requirement. All the margins are positive. That means all these items would be satisfactory. It should be noted the items listed here must be all satisfied. Any one or more failures would be taken as a failure of the stability check. In this slide, we examine the requirements of the dynamic stability. Here, a floating structure is subject to the wind. For instance, the beam wind. For the floating structure, we have the GZ curve, the curve A, and based on this GZ curve, we can easily obtain the maximum GZ max here. In the meantime, we have a second curve, which is a heating arm curve due to the wind, the curve B. These two curves have a cross point, which corresponds to a heel angle, and the writing value GZS. And we can now calculate the areas between these two curves. The area A1 here and the area A2 here. When calculate A2, we start from the heel angle phi s, and the calculation must cover an angle range of 25 degrees. See here. So for the dynamic stability, GZS must be smaller than 0.6 times of GZ max. The area A1 must be larger than 1.4 times of A2, and the equilibrium heel angle phi s must be smaller than 15 degrees. In this slide, an introduction of the ship stability in waves is made. When a boat travels following large waves, it seems the ship would travel faster. However, the ship following wave might lose its stability. In the small waves, the stability might be reduced slightly. See the black curve and the red dash curve. However, the longer and larger wave travels faster than the boat, and the large wave crest reaches the mid of the ship. It would cause a significant stability loss for the ship, and if the riding is long enough, a capsizing of the ship may happen due to the loss of the stability. You can see here, the red dashed line is the curve when the ship is riding on the crest of a large wave. When the large wave passes the ship might regain the stability, especially when the ship is between the crest of the wave. Therefore, in the cases of traveling in large waves, the ship should be heading into the wave Although it might be difficult, it is the correct way to maintain the ship stability in large wave. We know from the viewpoint of the stability, the larger the initial metacentric height, the better. However, in reality, very large GM might cause the large motion of the floating structure or unpleasant motion for people who are working on the floating structure. Or, in some cases, we may need the large responses of the structures in waves. For instance, the wave energy converter, so for efficiently extracting energy from waves. For the rotational motion, roll and pitch, their natural period is calculated as this expression. Here, I is the moment of the inertia. IA is the added moment of inertia. Hence, we can see the rotation natural period is inverse proportional to the square root of the initial metacentric height, Gm. In details, for lower motion, the natural period, T4, is given as this. Here, I44 is the transverse moment of inertia. AI44 is the corresponding added moment inertia, and GMT is the transverse initial metacentric height. Similarly, for the pitch, we have the formula for pitch natural period, T5. Here, GML is the longitudinal initial metacentric height. In reality, we may need to determine the correct GM so to satisfy the relevant standards and also to avoid the large motion of the floating structure in waves. In some practical cases, GM may be required to be small, so its corresponding natural period of the rotation motion would be much larger than that of waves. For instance, the floating wind turbines requires very small amplitude rotation motion, 1 to 2 degrees, and people on board dislike the rotation motion of the high frequencies. However, in the cases of the wave energy converter, they are normally designed to have large motions, so for efficiently extracting energy from waves. But at the same time, we may also try to avoid the motions of the wave energy converter, the motion modes which are not useful for extracting wave energy. For example, the rotating motions, the lower and the pitch motions in the point absorbs. In summary, we need to consider the stability of the floating structure, but also we need to consider how we can avoid or produce the large motion of the floating structure as required. For most of floating structure, they are designed to either have much smaller natural period than the most happened wave, such as the tension neck platform here. Their natural period would be much smaller than the wave period, or have much larger natural period than that of waves, such as the SPA or semi-submersible platforms, or even the FPSO, the floating production, storage, and offloading system, so to avoid the large motion of the floating structures. However, for wave energy converter, they are normally designed to have large motion with the wave, so for efficiently extracting energy from waves,